Imagine you could reach back in time and touch a moment that's already slipped away, a childhood memory, a world-changing event, or even the birth of a star. Most of us think of the past as something that's vanished, a collection of memories and stories that exist only in our minds. But what if the past isn't really gone? What if, as Richard Feynman suggested, the universe itself holds on to every moment, every action, every whisper of energy in ways that are far stranger and more profound than we ever imagined? Richard Feynman, Nobel Prize-winning physicist and legendary explainer of the universe, had a way of looking at time that was both unsettling and deeply inspiring. He didn't just see time as a river flowing from past to future. He saw it as a dimension woven into the very fabric of reality, inseparable from space itself. In Feynman's world, the past, present, and future are not as separate as they seem. And the clues to this mystery are hidden in the laws of physics, the behavior of atoms, and the strange symmetries that govern the universe. Let's start with the basics. In our everyday lives, time feels like a one-way street. We remember the past, experience the present, and anticipate the future. We can't go back, and we can't skip ahead. But the equations that describe the universe, the laws of physics, don't care about this direction. Whether you run them forward or backward, the math works just the same. This is called time symmetry, and it's one of the most profound features of the universe. Feynman loved to point out that at the deepest level, the universe doesn't distinguish between past and future. The fundamental laws, like Newton's laws of motion, Maxwell's equations for electromagnetism, and even the rules of quantum mechanics, are time reversible. If you filmed a collision between two billiard balls and played it backward, the physics would look perfectly normal. The equations don't care which way time flows. So why do we experience time as moving forward? Why does the past feel fixed and the future uncertain? The answer, Feynman explained, lies in the concept of entropy, the measure of disorder in a system. The second law of thermodynamics tells us that entropy always increases in a closed system. This is why eggs break but don't unbreak, why smoke spreads out but never gathers itself back into a match, why we grow older but never younger. Entropy gives time its arrow, its sense of direction. But here's the twist. The increase of entropy doesn't erase the past. It just makes it harder to reconstruct. The information about what happened is still there, hidden in the arrangement of atoms, the distribution of energy, the subtle patterns left behind. In principle, if you had perfect knowledge of every particle in the universe, you could run the equations backward and recover the past. The universe, Feynman argued, is like a giant computer, processing information in ways we're only beginning to understand. This idea is more than just a thought experiment. It's at the heart of some of the most exciting discoveries in modern physics. In quantum mechanics, for example, the wave function that describes a particle contains information about all possible pasts and futures. When we make a measurement, we collapse the wave function, selecting one outcome from many. But the other possibilities don't just vanish. They're encoded in the mathematics, in the probabilities, in the structure of reality itself. Feynman's own work on quantum electrodynamics, the theory that describes how light and matter interact, relied on the idea that particles can move both forward and backward in time. In his famous Feynman diagrams, an electron traveling backward in time is mathematically equivalent to a positron, the electron's antimatter twin, moving forward. This isn't just a mathematical trick. It's a reflection of the deep symmetries of the universe. Time, in Feynman's view, is not a rigid line, but a flexible dimension, full of hidden connections and possibilities. But what does this mean for us? Does it mean the past is still out there, waiting to be discovered? In a sense, yes. Every action you take, every word you speak, every breath you draw leaves a trace in the universe. The photons that bounce off your face travel outward at the speed of light, carrying an image of you into the cosmos. The vibrations of your voice ripple through the air. The heat from your body radiates into space. The atoms you touch are forever changed by your presence. The past is not gone. It's written into the fabric of reality, encoded in the patterns of energy and matter that make up the world. Feynman often spoke about the sum over histories approach in quantum mechanics. According to this idea, every possible path a particle could take from point A to point B contributes to its behavior. The universe doesn't just follow one history, it explores all possible histories, and the outcome we observe is the result of their interference. In this view, the past is not a single fixed story, but a tapestry of possibilities woven together by the laws of physics. This perspective is both humbling and empowering. It means that nothing is ever truly lost. The past may be hidden, scattered, or transformed, but it is never erased. The universe remembers even if we do not. And this memory is not just a metaphor, it's a physical reality built into the way the cosmos works. But Feynman also warned against the illusion of perfect knowledge. In practice, the universe is so vast, so complex, that reconstructing the past is almost impossible. The information is there, but it's scrambled, diffused, entangled with everything else. This is why we experience the past as gone, why memories fade, why history becomes legend. But at the deepest level, the past is still part of the present, still shaping the future in ways we can barely imagine. There's another layer to this story, one that touches on the nature of memory, consciousness, and the self. Feynman understood that our sense of the past is not just a product of physics, but of biology and psychology. Our brains are pattern recognition machines, constantly weaving together fragments of experience into a coherent story. Memory is not a perfect recording, but a reconstruction, a creative act that blends fact and imagination, reality and desire. Yet even here, the laws of physics are at work. The neurons that store your memories, the molecules that encode your thoughts, the electrical signals that flash through your brain, all of them obey the same rules, the same symmetries, the same relentless march of entropy. Your memories are patterns in matter, traces of the past preserved in the present. And as long as those patterns exist, the past is never truly gone. Feynman's view of time was not just a scientific theory, but a philosophy of life. He believed that understanding the universe meant embracing its complexity, its uncertainty, its endless capacity for surprise. He saw beauty in the way the past lingers in the present, in the way every moment is connected to every other, in the way the universe remembers. So the next time you think about the past, about lost moments, forgotten dreams, or vanished worlds, remember Feynman's insight. The past isn't really gone. It's woven into the fabric of reality, encoded in the patterns of energy and matter, preserved in the laws of physics. The universe is a vast, intricate memory, and you are part of its story. In the end, Feynman's greatest gift was not just his scientific genius, but his ability to make us see the world with new eyes. He taught us that the past is not a ghost, but a living presence, a force that shapes who we are and who we can become. The past is not lost. It's waiting to be discovered in the stars, in the atoms, in the very structure of the universe. And perhaps in understanding this, we can find a kind of immortality, not in escaping the flow of time, but in knowing that every moment, every action, every life leaves a mark that can never be erased. The past is not gone. It is part of us, and we are part of it forever.